and privileged to have Jamieson here today. He's on the faculty at the University of Washington. We actually tried to bring him to Stanford years ago, but he decided to go back to his undergraduate alma mater, University of Washington. He got his PhD at University of Wisconsin, working with Bob Novak, and then did a postdoc working with Benjamin Recht at Berkeley. And he's, I think, really special in this banded learning and community and reinforcement learning community, because he really brings together top-notch theoretical work and applied work where you actually try to get things working. And he worked on a number of systems. I think maybe while a graduate student or postdoc, he developed a banded learning system for selecting captions for the New Yorker magazine cartoons in the caption contest they have. And he's also worked on hyperparameter selection for neural networks and various technologies for A/B testing. Okay, so thank you for joining us today, Kevin.
Thank you for the generous introduction. So yeah, I hope I don't disappoint. I'm going to be talking about instance-dependent algorithms. I'll explain what that is in a moment. That's terms unfamiliar. Yeah, so first, obligatory slide of every RL talk. This will be an RL theory talk, so I'm not going to talk about any of these things today. But there has been a huge amount of success in RL, practically. But a lot of these successes have actually come from really intelligent reward shaping. Reward shaping being like you want to play chess, you want to win the game. That's what you care about. 0-1, win or lose. But to make the algorithm learn easier, you're going to assign maybe different weights to each one of the pieces that you get to sort of get the algorithm to have to sort of hint towards getting the right direction. And a lot of engineering goes into designing these really great reward functions for these different applications. And they try very hard to do this because if they make the problem easier, then basically any algorithm will work. Even very, very naive, uninformed algorithms that will just do like policy gradient or something like this will converge to a decent policy. But I mean, these are extreme examples of a huge amount of engineering work to get working. But it makes me think, what actually makes a problem easy or hard, right? If we're doing reward shaping to try to make this easier to learn using, with fewer samples and make it easier to learn, what actually makes a problem easier or hard in this world of RL? Because some problems are clearly easier or harder than others. If we have, if we're trying to get through this maze, an agent's going to have a lot easier time getting to the bottom one than the top one. It's very intuitive to us. But in the RL community, what we've become very attuned to, used to proving worst case sort of behaviors. In worst case, and meaning that the sample complexities or regret is characterized by basically the size of the instance over epsilon squared to find some epsilon good policy. So this could be like, say, the number of states and actions of the MDP in order to learn epsilon good policy. But because they're easier and harder, these mazes have the same states and actions, but one is easier and harder than the other. And so what I'm interested in doing in this talk and in general in my work is trying to understand what are the specific properties of the MDPs. Is it the state transitions, the reward function? How do we change these things in order to, what makes a problem easy or what makes it hard? And once we characterize these different attributes of the MDP, how do we design algorithms that exploit these properties? So when the problem is very easy, if the MDP is easy, I want my algorithm to take advantage of that easiness, and I want to provably do so. And when it's hard, well, I'm never going to suffer worse in the worst case. And one bigger theme throughout this talk is going to be, what does optimal exploration even look like? How should we be exploring MDPs in order to learn the reward function of the transitions effectively and as fast as possible? And so we're going to talk about basically three works that have developed over the last few years towards this end. And I'm going to be focusing on three different kinds of exploration. These are three very different strategies for exploring reinforcement learning problems, starting with optimism, axial elimination, and policy elimination. So these are three different papers towards very different ends, but they're kind of unified in their goal of developing better exploration. So this first work is going to be on regret minimization. And is with Max and Joyce at MIT. So the problem that we're going to be studying throughout this entire talk is going to be an episodic RL problem in the tabular case. So we have some agent, we have some environment, some initial state is drawn from the environment. The agent reacts to that state with an action, playing according to some policy. The environment then responds to the reward in a next state. Okay. And then in response to this next state, the agent takes another action, and then a next state comes again, and the next reward comes again. And this process repeats for H time steps. Okay. So this is one episode is carrying out this for H time steps, and then the episode restarts. And then we get to play a different sequence of actions. And every time you play a state, you get this random reward, and you're transported to a random state, this next state. And we don't know in RL what these rewards are or what these state transition matrices are. So we don't know how we're going to move or what state we're going to be transported to, and we have to learn that online while also trying to accumulate as much reward. Some brief notation. We're going to define the policy of pi, the value of the policy pi as v pi, and it's just going to be the expected reward achieved by policy pi, meaning if I were to roll out policy pi, what's the expected amount of accumulated reward I'm going to get over this episode? And then by v star or v pi star, where pi star is the optimal policy, it's going to be the value function of the policy in my policy set that achieves the largest amount of reward. And then we have the standard notion of regret, which is after k episodes, I want to compete with the best policy, whereas at each time little k equals 1 to k, I play pi k and get value v pi k, whereas the optimal policy plays pi star and gets v pi star. To ground this, if it helps to have sort of a picture in your head, you could think of having a finite number of states in sort of grid world. This little sailboat sailing around this grid world, he can go up, left, right, or down, but maybe there's some wind that stochastically sort of perturbs him. So if he tries to go up, maybe he actually goes right. And then there's little gold coins strewn throughout the state space, and he has to go and find those. And so the problem then is, after these H time steps, he wants to accumulate as much of this gold as possible, but he doesn't know where the reward is, and he doesn't know what the wind's going to be. A really fundamental quantity is going to be this gap parameter. And what this is basically we define QH of SA. This is going to be the value achieved if you start in time H, you play and at time H in state S, you play action A, and then you transition to the next state and you follow the optimal policy from then on. Okay. And then v pi star S is just the optimal value function if you started in state H. Okay. Any questions on this notation?
Aren't there subscript zeros on some of these V's and not others?
Sorry, ignore the zero. Ignore the zero. That doesn't mean anything. Core notation, sorry. It's meant to symbolize that when it was zero, it's not, it could be one. Yeah, ignore the zeros. Okay, so MDP is 101. We know that the optimal policy satisfies the following equations. And it can be solved for using dynamic programming, where we have the reward function here, RH of SA. We define that we put our Q star equal to that, and then we go back in time of just iterating this procedure all the way back to time equals 1. And then once we have this Q function, we just maximize it at the greedy action with respect to this Q star function. And this will find the optimal policy. However, yeah.
Use a fixed horizon.
Yes, exactly. It's always going to be a fixed horizon capital H, and it's not going off to infinity or anything like this. And once I get to the end of that episode, I restart the episode at time 1. So anytime I'm playing some policy or playing this in the real world, I'm going to have some empirical data, but I'll never know what the true reward function and the true transitions are. And so what can I do with this information? Well, what optimism does, this first strategy that we're going to look at, is it just plugs in those empirical quantities, but then adds a little bit of a bonus. So this BHK of SA, they're going to add it to every one of these Q functions. And the purpose of this little bonus is to make it so that you're not playing too greedily. If you didn't have this bonus, you're playing too greedily with respect to the empirical thing, and you can get yourself stuck in a corner and bad things can happen. But if you put this bonus here, you want to choose this such that for all S, A, and H, this Q bar is always at least greater than or equal to the Q star, H of SA. And I can choose this bonus just basically using standard confidence bounds and things like this. I know the statistics, so I can choose this B bonus without actually knowing what Q star is. But I'm not going to get into exactly what the form of these things are. But to give you some intuition of like why this strategy should ever work is we can go to multivariate bandits. So in multivariate bandits, you have A actions. You just have, it's an MDT with one state and one horizon, the simplest possible situation. And if you have A arms, then you're going to pull every one at once, and they're going to exactly play optimism. You're going to construct your empirical rewards for each one of your A arms. You have NK of A, the number of times you played that eighth arm, and you're going to play some strategy that looks like this. And when you get the reward, you're going to update the empirical reward and the number of times you played. And if you simulate this, what it's going to do is if these little lines here, these confidence bounds, these bonuses, you'll see that it's going to play out. And the best arm here is confidence intervals. We design these things so that the empirical mean is always within these confidence intervals, and the true mean is as well. And so this confidence interval will never go below the highest mean. But if I keep pulling some other suboptimal arm, its confidence bound will go below the top mean, and then it will never be played again. Right? It cannot be played again because what it's doing is it's playing the arm with the highest ever confidence bound. And eventually you'll only be playing the best arm. And it's quite easy to work out what the regret of the strategy is, like how much regret am I incurring from a single arm A. It's just going to be the regret of playing that action times some indicator of does my confidence with the confidence cannot get less than the gap between the eighth arm and the optimal arm, and we're just waiting for that to happen. And so we get this nice sample complexity that's scaling, or this nice regret bound that's scaling like the minimum of some worst case minimax sort of sample complexity is square root of AK. So it's totally independent of what the means are. The means can be arbitrarily bad or small, doesn't matter. You're never going to suffer more than square root of AK. But if the means, if we're in a good situation, if the gaps are actually very, very large, then I'm going to be able to figure this out. I'm going to figure out what the best arm is, and I'm only going to suffer logarithmic effect. I'm going to scale like log K. Okay. And the point here is that these gaps are properties of the specific instance, the specific means of this particular multivariate bandit problem. And what the goal of this talk is going to be about is basically what are these right quantities for RL? What are the quantities that we want to have here? What are the instance-dependent quantities that are going to govern the regret and the sample complexity of learning in MDPs? It is well known by a number of authors, and there's way more here than I can list in different settings. But it's well known for MDPs that the regret, if you run optimism, an algorithm just like this, achieves a nice minimax guarantee of root K. And the H cubed SAK, depending on whether you're stationary or non-stationary, but these are details. I really just want to focus on whether you're getting root K or log K. But we call this a minimax bound or a worst case bound because it just depends on coarse quantities like the number of states and actions and the horizon, not the individual state transitions or rewards themselves, not the gaps. And so the question is optimism also optimal? Or does it achieve a gap-dependent complexity, just like optimism does for bandits? Is optimism also optimal for MDPs? And the answer is yes, with some caveats. So we actually analyzed an algorithm called Euler by Zenet and Brunskill, designed here at Stanford. And it's an existing algorithm. It's a great algorithm. I love it. And we just analyzed this, and basically through some tricks and things, we showed that you can in fact get a regret bound that scales with the inverse gap, with some of the inverse gaps, just like the bandit problem. What's interesting about this is that you don't the state visitation probabilities or the transition agencies don't show up explicitly in this formulation, just the gaps, but the gaps are the gaps in those Q functions, so they are sort of implicitly in there, just a little hidden. And also throughout this talk, I don't want you to focus on like exactly what the regret bound looks like or the pack, or exactly how the algorithm works. I want you to more focus on like what's the sort of higher level story of how these algorithms are exploring, how they differ in their strategies. Because all these constants and log factors, they're not going to be very important to the story. Well, because we're analyzing an existing algorithm that's minimax, we immediately give this algorithm minimax. This term here is annoying, but it's actually unremovable in general. And it matches lower bounds for a large class of MDPs. We cannot claim that this is optimal for every instance. And the reason why is that we can prove information theoretic lower bound on the regret. However, the actual lower bound that you get out, that regret, is the solution to a non-convex program. So if you wanted to hit that, you'd have to get around solving a non-convex program in your algorithm, presumably. And so we can't do that, or we're giving up on that. But we can compare to this large class of MDPs that are not going to define. You can read the paper, and we do match all those lower bounds. So we're pretty confident this is tight, and I'm calling this optimal for the rest of the talk, but we can split hairs on that. So at the end of the day, we get this very nice regret bound. This is what optimism gets us. But what I really want to talk about this in talk is not about regret. It's actually about sample complexity. How many samples does it take in order to identify policy that's epsilon good? And if you're keeping score, optimism was optimal from a worst case and instance dependent case for bandits, and also for MDPs. Okay, so optimism so far is looking like a really, really good algorithm. But we're going to see in a moment that it stays unnumbered.
Kevin, just so I can understand, when you say instance optimal theory, so in the Lyon-Robbins paper,
Yes, in the Lyon-Robbins sense.
In the Lyon-Robbins paper, they say any algorithm that achieves sublinear regret, or what do they say? Any algorithm that achieves sublinear regret or logarithmic regret?
Any algorithm that achieves regret less than or equal to n to the alpha for some alpha between 0 and 1.
Right.
Subpolynomial.
Has to suffer regret at least some of log beyond.
That's correct.
And that's the same optionality notion. Is that also true for MDPs, that anything?
Yes. So you can. So that this will, if you
Basically just the same lower bound construction works essentially, or sorry, go ahead.
same tools. Yes, the same tools are the same. But it's significantly more. It's a little more complicated, but yeah, it's the same set of tools and it's the same sort of assumptions.
Okay.
And that lower bound that pops out from that style analysis is the solution to a non-convex program.
See, these inequalities earlier with the min between square root of QT and 1 over delta log something. I didn't see the big O or anything. They're all.
Oh, okay. Yes. I'm going to be very loose with
Probably full of one time.
not even that, like it's actually like there's other disgusting log factors here, or this looks very, very pretty. In the real expression, it's this horrible thing that would take up the entire screen. But this is by far like the dominant term, and it's the thing that if you were to prove a lower bound and where you get very nice things that come out, that's the leading term, and that's what I'm going to put up here. But there is a lot of other stuff that matters, but is insignificant. It's not stuff that I care about in this talk, but I might in the future. I don't know. RL is hard, so. For this result, no. The only reason we use Euler versus Azar et al. Is because we just wanted the tightest variance result in our bounds. I could have achieved this if we used any other MDP that got root K. Optimism is very, very general here. It works for basically any optimistic algorithm. This is all.
So I presume you know this, but as a practical matter, like these optimistic algorithms don't work very well.
Yeah.
Okay, so the notion of optimality here is pretty loose.
Oh, yeah.
Okay.
Large constants and it's
It's more than confidence.
we're gonna,
Practical.
you mean in practice?
Practice.
Yeah. Yeah, it's hard. I mean, yes, I'll have to take your word for that. I mean, I've only implemented a few of these algorithms, and in my experience, nothing seems to work.
Well, it feels like you're using a primitive starting point.
Mhm.
The notion that you induce an optimistic boost at each direction pair with no interdependencies between what you introduce across the election pair.
So I am assuming, well, these optimistic algorithms are just adding a single bonus to each SA, but inside this term can depend on other information collected from other states. Because this is
I understand
capturing
that.
uncertainty on future states and things as well.
Yeah, I understand that, but there's no notion that in this episode, if I'm gonna be very optimistic about this essay, I better not be so optimistic on that one, because lightning doesn't strike twice.
That's true. Can be a pretty coarse analysis. Okay. So I'm really going to care about sample complexity. And so this is another paper with Max and my student Andrew at UW. And we're studying the sample complexity of identifying an epsilon good policy. So same setup as before, but now instead of doing regret, we're going to change the game. I'm going to say, I don't care what you do. I don't care how much regret you're accumulating on the way. All I want at the end of the day is for you to return some policy pi hat that's epsilon optimal using as few total interactions with the environment as possible. Okay, so I don't care how much regret you're incurring to get here. I just want you to return some pi hat to me at some point in the future if you're choosing, and that time is supposed to be as short as possible under this guarantee. So we have this regret result. Can we leverage this? Yes. So there's something called the online to batch conversion. We've run it for a long time. I have a citation here, but they definitely did not come up with it. First, basically what it does, it's a very simple expression. It says, if I have a regret bound, I know that from little k equals 1 to the k, that it's bounded by some function rk. Then if I choose pi hat uniformly at random among all those policies that I've seen so far, then just a direct calculation of the expectation of v pi hat, you're going to get that v pi star minus v pi hat is going to be less than or equal to r of k over k. Okay, it's a very coarse sort of thing. It's not a great idea to do. I wouldn't recommend it, but you can do this and it'll get you a pack bound. And by applying this directly to our result here, a direct corollary is going to be that we get some sample complexity, which I'm calling pack of epsilon, is less than or equal to some overall SAH of the min of 1 over epsilon times the gap and 1 over epsilon squared. Okay. This is good news. This is good news for one thing, because I know from other papers that people have published, including Azar et al. And Brunskill, we know that the minimax sample complexity for tabular, for pack learning, is SA over epsilon squared. And so we're immediately getting that. Okay. And we already knew this. We know that optimism will achieve the minimax rate of 1 over epsilon squared, of SA over epsilon squared. And so again, if you're keeping score, for bandits, I didn't tell you this, but I'm telling you now, then bandits optimism, a single algorithm, is actually optimal up to constants and things in log terms for all these problems. It's optimal for regret and pack simultaneously. Just run UCB with a little bit of inflated confidence bound. And for MVP, I just told you that for pack, this SA over epsilon squared is tight, or it's minimax optimal. And so that's great. We have this nice check mark here. And the question is it also instance dependent type? Meaning, is this term here, is this the exact expression such that we could never hope to do any better than this? There's no other sort of, depending on the other gaps or depending on the state of the changing probability, is this really the core sample complexity expression? And the answer is no. It's actually quite loose. And so the remainder of the talk is I'm going to go through two different algorithms in two different attempts to try to hit the right instance-dependent sample complexity. And this is going to require very different algorithms, how to get there. Okay, so if you didn't like me hiding stuff before, you're not going to like this. So there's a lot hidden here. But I really want to focus on is this sample complexity is dominated by the speed of epsilon. I'm telling you that. And that's what I want you to focus on. This is the main term that's going to eat all of your samples. And it's defined as this. And I don't want you to stare at it because it's very complicated. And you're not supposed to I haven't defined notation in this yet for you. But over the next 5 minutes, I promise you, you're going to look at this thing and be like, oh, of course, that's the answer. If everything goes right. So a few words, though, on this theorem. First, we recover minimax optimality. This algorithm that I haven't told you what it is yet, it is minimax optimal. It's always tighter than the online to batch conversion that the optimism gets. So in good shape there. And also there's some prior work here that looked at exact policy identification, where epsilon is equal to 0 and asking product is little delta goes to 0. We match all that. We match that bound in a non-asymptotic rate. So everything's looking pretty good. And so you want you thinking though, the natural question is, I have this algorithm optimism, seems pretty good. It was optimal for bandits. All the boxes were green. Maybe it's just a bad it's a good algorithm, but a bad analysis. Maybe I can do better. But no, you can't. There exists an instance that I can create such that if you played optimism on this instance, to find an epsilon good policy, it's going to require 1 over epsilon samples, whereas mocha, this algorithm, will return a policy in a constant number of samples with respect to epsilon. It will depend horribly on the number of states and things like this, but I'm just caring about the epsilon dependence right now, so because I can make epsilon as small as I want. And the intuition for why optimism fails is that optimistic algorithms are very greedy in a way. They're trying to seek out the reward and sniff it out and follow that reward signal. And as soon as they figure out that an action is suboptimal, they're going to stop taking it. But you could be in a situation with MVP where you could take some action that gets very, very bad reward. It's a terrible idea to go to this part of the state space. And so an optimistic algorithm will only go there a couple of times and then stop because it's just a terrible idea for accumulating reward. But mocha or some algorithm that's planning for the future might go to those states and realize, oh, but if I go here, I gain access to the rest of the states really easily. And I can explore the MVP super easily. And so I'm going to keep going back to this state that gives me access to the rest of the MVP. And it's this planning that allows us to get these tighter rates. So let me go through. Yeah.
Question. So it seems like your original optimistic algorithm also serves that purpose. If there's a part of the space that accesses a lot of the MVP, especially parts of the MVP that are uncertain, bonuses based on that uncertainty should propagate back to the undesirable part of the space. So why does that already take care of the issue you're talking about?
Great question. So it will. The optimism bonuses will make the agent go to those states. It will explore them a little bit, but very quickly it'll figure out if these are very, very bad reward states. It'll very quickly figure out that they're suboptimal. The bonuses will shrink below that top action, and then the optimistic algorithm will stop taking those actions.
So you say I guess you mean you become confident that under an optimal policy you would never go there.
Yes.
But yet, when you're exploring, it's helpful to go there.
Exactly. So let's go through the algorithm. Let's return to bandits for a second, because in type MDP, they are really bandits at their core. It's kind of like having an independent bandit at each state and time H. And if I just want to find an action, one of my A arms that's epsilon good, where the gap is less than epsilon, there's very simple algorithms out there, including this elimination style algorithm. It's very simple. I maintain an active set of arms, I uniformly sample these actions, and discard an action as soon as its confidence interval is below any other arm's confidence interval. Because then I know that that action cannot be optimal because I found some other one that its confidence interval is completely above it. And the true actions mean is inside these confidence intervals. And then we keep sampling until all the remaining actions in their in that active set are less than or equal to epsilon. The confidence interval is epsilon. And it's not hard to show. It's a nice exercise to show that you can achieve a sample complexity that scales like the sum of the inverse gap squared and 1 over epsilon squared. Okay, and really all this is doing is how many samples do you need to pull an arm to get its confidence interval of 1 over root n less than the gap. That's it. And like I said, tabular MDPs are basically like bandits, and so maybe we can use this algorithm. But the problem is that it's different in that I don't care about finding instantaneous rewards at any given state. I care about the whole reward I'm getting throughout the entire trajectory. And the current action also affects current future states, But most importantly, some states are very hard to get to. Some states are just impossible to get to. And I have no hope of the optimal policy getting there because no policy can get there just because the probability of transiting to that state from any other state is very, very small. And so a key piece of our analysis is going to be the state visitation probability. Okay, so this WH pi of S, take a moment and stare at that for a second because it's going to come up a lot. And what it is just the probability that when you're playing policy pi, that it visits state S at time H. Okay, so WH pi of S is the probability that policy pi visits state S at time H. Yeah.
There's a question from the chat.
Yeah.
He's asking if optimism is not instance optimal for a linear bandit.
It is for this is all tabular. I haven't said anything about linear bandits, but it is true that optimism is not optimal for linear bandits. So it turns out you can prove by doing sort of a standard perturbation sort of analysis, is that it really only suffices in each state in horizon H. You only really need to learn the optimal action in that state in horizon up to tolerance epsilon over W pi star H of S. Okay. And what this means is that if it's really, really hard to get to a particular state at some time H, by the optimal policy pi star, if that policy is just never going to go there, I don't need to learn that state. I really just don't need to know what the optimal action is. And it turns out that this nice weighting is if this is a very, very small number, it means that the tolerance I need to learn that state is extremely large. Because what you should be thinking here is if to learn an epsilon good arm in bandits is 1 over epsilon squared, if I only need to learn epsilon over W pi star of H, which is much, much bigger than epsilon, then I can potentially get a huge savings here. Only problem is, I don't know what pi star is. So I definitely don't know what W pi star is. Turns out though, that it's quite easy to estimate what the maximum policy's visitation is. So for every time H in state S, there's some policy out there that visits this state at this time more than any other one. And estimating this quantity is actually pretty easy and very efficient. And so what our algorithm is going to do is instead try to learn each state in horizon H up to tolerance epsilon over the soup over all policies pi. Yeah. No, it doesn't. We'll see in a second. So first, how are we going to run this algorithm? This is the mocha algorithm that we've been talking about. How does it work? So I want you to fix some policy pi in. Don't worry about what it is. It's just some policy pi in that's going to be an exploration policy. but don't worry about exactly what it is right now. Just imagine a policy that visits every state in action with some small probability, let's say. And we're going to go all the way just to this last time instance, time h. And at this time h, this is a very special time because there's no more states after this transit to. You're just sort of getting a reward at this state and then moving on in your life. And so here it really is a bandit. It's exactly a bandit. And so we exactly get to solve this state, to find an epsilon good policy just at this level h is just going to be the sample complexity here that we saw with the action elimination of on the previous slide, because it is just a bandit. However, it takes some amount of time to get there. So W pi in, this is again the probability that pi in visits state S at time capital H. And if that's a very small probability, or that's some probability, to get there once, I should go there at least the inverse of that probability. And so this is going to have to show up, and I have to get to all the states, so it's going to be a max over S. And there are details here that I'm glossing over. It could be that you can't get to some states, and we filter those out. And so this is never going to be infinite, but glossing over details. But then we're going to lock down this policy pi hat at this time, and then go back one stage. And now, once I've locked down this policy, now if I take some action in this state, it's then going to go through this process and then play pi hat, but it's a fixed process at that point. So all I've done is I'm really just back to a normal bandit again at this state. And I repeat this process over and over. I go all the way back until I get a sample complexity that's the sum over all H and this sample complexity. Okay. And so this looks familiar because it's exactly the sample complexity that I showed you a few of epsilon. This is where it all comes from. And the big question then is, where does pi in come from? How do you find this great policy that somehow achieves the int over all pi instead of just some arbitrary pi in? How do we achieve that? And it's actually kind of cool. We leverage two works in particular. This Jin et al. And Zhang et al. Jin uses Euler in a very intelligent way to try to get to rare states. And Zhang does a very, very nice sort of clustering of states that are easily reachable together. We sort of marry these two algorithms to get our theorem to be able to find this pi in and do it as well as possible. But really, if you're familiar with the R max algorithm, it's basically inspired by that. That's what this procedure is doing. So it's just trying to get to states. Okay. So for this epsilon optimal problem, we saw that optimism gets this sample complexity, and this algorithm mocha gets this sample complexity here. And I showed you that this is always better than optimism. And I want you to take a second to review like what these algorithms are doing. Optimism is trying to model the dynamic programming, and then trying to do these bonus rewards, and then going all the way to the back, and then pulling it forward in time. Action elimination is doing the exact same thing, but it's doing it in a much greedier way. It's going all the way to the end time h, solving the problem there, and then moving backwards. Meaning it does not proceed. It doesn't even care what's going on in the beginning stages until it's solved the last stage and then marches back forward. And so these are very, very different algorithms. And you might ask, what is this tight? Again, lower bound is a non-convex problem, but we can relate it to a bunch of instances that shows that it's reasonably good. But a lot of times, both these algorithms assume that all policies are accessible, meaning every policy, in every state, I can take any action I want. And a lot of times this is completely unrealistic. In the real world, when we're working with robots or we're working with like ride sharing type situations, we have some policy that engineers worked very hard to create, but they acknowledge that these policies have some parameters and some tuning knobs. And so then they create additional policies that they just don't know what's optimal, but here's a set of policies that I consider to be pretty decent, find the best one among these. And so a natural question then is to ask, given a finite set of policies, how do we find one that's epsilon optimal just within this policy set, this finite set? And this should be strictly easier than these other problems because I've restricted you to a smaller set of policies. And indeed it is. But I can always relate this problem back to if I let big pi be all policies. So, but we're going to take a moment to study this problem. So now big pi is a finite set. So one thing you notice immediately, if you're thinking about this problem, if you're like me, is that you try to relate back to simpler problems. And if you're familiar with contextual bandits, where you have big H equal to 1, we don't know the answer to this question. Until a few months ago, we didn't know what actually that optimal sample complexity was for instance dependent. So we had to go and write that paper first. And with some brilliant co-authors, we figured that out. And for this, there is no non-convex lower bound. It's a convex program. We can solve it, and we in our algorithm can actually relate to it. We're hitting the lower bound for contextual bandit. But this talk is about RL. And so we went on to study this problem of how do we find the best policy within this finite set in MDPs. Now, I'm going to be studying the tabular environment, talking about it here anyways, but this paper is actually more general. It's actually for the linear MDP setting, if you're familiar with that. And again, this is work with my student Andrew. And yeah, if you want to hear Andrew talk about the linear setting, he's actually in the Bay for the next few months. So, okay. This strategy is going to be a little different. And it seems so far. And the way that we're going to start is we're going to write down exactly what the value of the policy is. Like I said, it's just the expected reward of if you rolled out policy pi and the expected rewards you get along the way. Well, if I define WH pi of S prime A prime as the probability that policy pi plays action A prime in state S prime at time H, then if I define it that way, then what this is doing is just a straight up calculation of the expectation of the value function. And we get this quantity here. It's just, and then we can write this as, if we think of these things as vectors, the state action visitation probabilities and rewards, and then it's just the inner product of these two. Okay. So think of WH pi and RH as vectors now. And while these WH pi's are kind of complicated objects, they can be computed recursively. You can just initialize through the initial state distribution what W1 is, and then you can push forward what WH is, going from W1 to W2 to W3, W4, on just like pushing it through the transition operator. And so this is very well and good, but we don't know what P is, so we're going to do the plug-in estimate of P hat, and this tends to be pretty good. And so now this algorithm is going to be a little different. And then instead of starting at the end, which both optimism and action elimination does, for policy elimination, we're actually going to start at the beginning. We're going to run in some policy pi in, and we're going to start at the beginning. And we're going to start to estimate W hat 1 and R hat 1, just as we were doing on the previous slide. And that's not going to take many episodes. Just A over epsilon squared, log pi. This is familiar because this is just the contextual bandit rate. And by the way, this is going to take some input epsilon 1 and the initial set pi 1 equal to big pi. Now, once we've solved for W hat 1 and R hat 1, we're then going to push that measure forward through the transition operator, and we'll get some sample complexity like this. The number of samples to learn W hat 2 is going to scale like basically this. You can think of this as almost like an inverse propensity score of the previous state action visitations. And like how mismatched is your pi in versus the policy pi that you're trying to estimate. And then we can repeat this, just keep pushing W hat all the way through the MDP. And then once we do that, we're going to have our estimate for V hat pi of just the sum of all little h equal 1 to h of this R hat h and W hat h. And the way that we define these sample complexities or our tolerance to each stage, we'll have the whole thing is going to be less than epsilon 1. And you're estimating each policy value of epsilon 1. And then we'll do elimination. We'll just, any policy that is greater than 2 epsilon 1 off and its empirical value, we're going to discard it. And then we just have pi 2 in the break. And we're going to now have epsilon 2 and then repeat this process all over again. And repeat it log 1 of epsilon times. And then when we do that, we're guaranteed after log 1 of epsilon steps of this algorithm will be guaranteed the output of epsilon policy. And so the final sampling complexity, when you add it up, scales like this. Where now, in the denominator, you have not the individual gaps of the states and actions, but actually the difference in the value functions themselves. And how do we, we had to learn pi in somehow. How do we do that? Similar, but in a different way. We actually treat this as an external design problem, like you would with a linear external design. And one way to solve those problems is to do Frank-Wolf. The difference, though, is in a linear external design, you know what vectors you can measure, whereas here the analog to vectors is state action visitation probabilities. You don't know what those are, so you need to run some very clever algorithm to do that. It's a very cool part of the paper, but it's very technical, so I'm not going to go into it. But anyways, this is how we achieve this n sample complexity. And so I just want to again sort of bring us back to like what are the different strategies here? This optimism was trying to just sort of greedily go after these bonuses. Action elimination was trying to go to the last stage and really eliminate and then move on and march all the way back. Whereas this policy elimination strategy is pushing forward. And the interesting thing is that while these two are dependent on the gaps themselves, the state actions gaps, this one is dependent on only the entire policy's value. So the natural question is, if I apply this algorithm to the set of all policies, which one's tighter? Which one's better? Fortunately, neither. There exists two MDPs, M1 and M2, that I can create such that there is this terrible matrix where one of them is going to have to pay a lot and the other one. And the way you construct this is really easily, you basically construct these MVPs where in one of the MVPs, the value gap is really large, and that last state has really, really small gaps. But by the time you got there, the early stages already made it obvious what the optimal policy was. And so the action elimination strategy was just killing itself by spending all this time there. And the other MDP is similar in a different flavor. So this is exciting. I mean, there's open problems to be solved here, but what I'm excited about this is that these are three sort of very different ways of exploring MVPs, and they really get different sample complexities, and there's still a lot more work to be done. And so it's very encouraging to me. It's a very exciting time to be in this field because I just don't know what the answer is. I don't know what the right sample complexity is. I can't guess it. Gun to my head, I really couldn't even guess. Maybe this is supposed to be W pi star, not the soup. Maybe this is actually supposed to be the differences of WH pi and WH pi star. Maybe. But like, I really don't know the answer. And I love working on problems where I don't know the answer. There's a bunch of open problems, but I'll stop there. Take any questions.
I'll ask a question. So, a story you told, which was very interesting early in the talk, about how what you wanted was to frequently visit places where you could access all the states from, so you could learn about all the other states.
Mm.
Right? Even if an optimal policy would not go to that, not that part of the state space that lets you access everything else. That makes a lot of sense. And if I take an algorithm like your mocha algorithm, it feels like it's doing that and it's accessing all these states, but it also feels like it's accessing all these other states, even if accessing all these other states has no chance of helping eventually, right?
Yes.
It feels like there's a lot of
That-
waste there.
There's a lot of waste.
Got it.
And that exactly right. You intuitively, you really shouldn't have to go to states in which the optimal policy will never go to. Or you don't need to actually learn about those states at least. Maybe you need to go there to access other states, but you don't need to learn about what's the optimal action in that state. And really, this comes from the fact that we don't know. Yeah, it goes back to, I'm not going to find it now. Transitions are killing me. But it goes back to the fact that like we only need to learn each state up to this tolerance of W pi star over epsilon, and not this soup over it. And so we take this very worst case approach of like, well, I don't know what that is. So, you know, pi star is one of the policies. So I'm going to assume that in the worst case, and have to really cover myself. But it's extremely risky. And there's a lot of slack that can be done in algorithms to clean that out. But it does seem like, at least intuitively, the policy elimination style algorithm, the fact that this one here, the fact that you're decrementing epsilon 1, you do this first forward pass with a very coarse epsilon 1. And then after you finish that first pass and remove policies, then you have epsilon repeat this. And this sort of incremental approach seems like the better one than the mocha algorithm, which really like bets everything on solving every state. It's just too aggressive and too locking on to an objective. But we know from the result at the end that like it has its issues too. So it's not clear if you can come up with it's not clear how to come up with an algorithm that will achieve sort of the best of both worlds, but is it, you know, a normal algorithm that's very natural.
Can you maintain a set of policies even if they're infinite?
Yeah. Okay. So for mocha, yes, we can maintain them, and we never need to explicitly maintain them, and it's computationally efficient to run that algorithm. For the policy elimination algorithm, we don't know how to do it without maintaining a set of policies. So it's not a efficient algorithm if you're considering all policies, because you'd have to enumerate them.
Oh, yeah, but like even if we are willing to throw all compute at it, there are potentially an infinite number of policies. So can you even like store them?
Yeah, so we'll let our exploration policy be stochastic, but we're going to search over deterministic policies. And there's only a finite number of those. Because we know that for the true MDP, the optimal policy is a deterministic policy. And so we're going to constrain ourselves to searching over just deterministic policies, but our exploration policy that's getting us data, that will be stochastic and necessarily stochastic.
Just like one. This is because it's a finite state space and
Yes, finite states and actions and horizon. You ignore horizon somehow.
Nothing from the remote. Thank you so much. One more question. I'll say all your questions.
I guess like the optimistic algorithms, like also like simultaneously have a regret here. So I was wondering, like among the class of algorithms that also have like a log regret, is like optimism the best you can do for also being a factor.
I don't know if optimism is I can't say it's the best algorithm within the class that gets both optimal regret and minimizes sample. It's a great question. I don't know. I do know that there is a fundamental trade-off though. In all these papers, we have to have some theorem in there that shows that we say something stronger than just optimism. We say any algorithm that gets low regret necessarily gets suboptimal sample complexity, and it could be usually unbounded worse. And so you cannot have an algorithm that's optimal for both. We know that, but that's a really interesting question. Like, is among the class of algorithms that gets optimal regret, what is the best analytical place that they can achieve? I don't know. Great question.
And for that problem, do you always assume the online to batch conversion?
No. That's also a great question. No, we don't. We don't assume that. It's an information theoretical argument. So it's.
Thank you very much.
Thank you.